I welcome all the participants and I welcome Janni ma'am for this particular penultimate day of our FDP QT-05. Ms. Janni has an MS in research from ISR Pune, and today she has agreed to take this particular session for us. Thank you, ma'am, for taking time out of your busy schedule and enlightening us with specific topics of this quantum program. Thank you.
Good afternoon, everyone. Thank you, sir, for your kind words. I'm happy to be here, and I hope we can discuss. Today, we're going to discuss the topic, near-term quantum processors and the topic of quantum circuit compilation, which is extremely essential. We'll discuss it more in detail once we start the session. Yeah, let's get started then. I'll share my screen. I hope it's visible.
Yes, ma'am. It's visible.
Okay. So the plan is to basically have two sessions. Like the first one, we will discuss about some near-term processors, like the journey so far. What have we seen? What is a first of all is a quantum processing unit? What are its components and some details related to that? And because this is a course mainly on quantum computation and it's related to quantum algorithms, we have to ultimately think about whatever quantum algorithm you're developing, how are you going to implement it on a quantum computer, right? And to be able to implement a quantum algorithm in the near term or in the utility era, right now it's the utility era and we are going towards fault tolerant. However, there are many requirements to be able to map a quantum algorithm to run on a quantum computer. So one of the major requirements is quantum circuit compilation. Like we'll discuss the pipeline in the second. We'll discuss the major aspects of how we do quantum circuit compilation and why it's necessary for, say, going from a quantum algorithm to implementing it on a quantum computer. Actually, why it's extremely essential. So we will discuss that in the second session. So, a very short intro of myself. My name is Janani. I am a quantum engineer at IBM, part of the quantum team at IBM Research Bangalore, and I'm part of the technical support team. So, yeah, let's get started. So, what are the lecture objectives and takeaways? So, I would say there are two main objectives. One is to understand the basic architecture of a QPU and whatever chip is inside it. So, what is the advancement that we are making as time goes, right? We come out with new hardware, and we have to. And accordingly, so building a quantum computer means you have to build the components which make the quantum computer, and the main component would be the chip inside it. So we will understand the basic architecture of what makes a QPU and the chip inside it, and basically the journey that has been happening going on so far. And the second part of the lecture, I hope everybody gets to understand the basics of quantum circuit compilation, or as we call it, transpilation on different QPUs. So basically, why is quantum circuit compilation? It's not just necessary, it's a must, it's an absolute. Without it, you cannot really think very deeply about how you're going to implement a quantum algorithm on a quantum computer. And we will see and we will discuss why. Specifically in the context of whatever algorithms you might have learned so far in this course. So in that context, I think it's good that we are having this discussion at the very last day, because you would have come across Shor's algorithm, QAOA, VQE, and which are both variational, of course. And you would have come across the more basic but very pure and fundamental quantum algorithms like quantum phase estimation, quantum Fourier transform, etc. Right? So why is quantum circuit compilation absolutely necessary to be able to implement them, to be able to implement these algorithms on a quantum computer? So transpilation is a complex process. It's not it's not a simple process to understand in maybe one lecture. However, I hope that you get a generic idea of what we do during transpilation and why it's an absolute must, essentially. So just to say, if any of you have any questions, please feel free to interrupt me, or if you're putting it in the chat, please someone let me know, because I cannot see what is being written in the chat. So in case you have any questions, please feel free to ask me at any time. Like, I don't mind taking questions in between the lecture. So let's get started. So the first part, let us start with the most basic question. What is a QPU? So a QPU, which stands for a quantum processing unit, is a state-of-the-art processing hardware that uses qubits or quantum bits to solve complex problems by using quantum mechanics. Now, I mean, like, this is QT-05, and you guys have been like, and this whole course you've gone through like learning so many more advanced topics on quantum computation. But why is it necessary to stay this still at this stage? Because like, this is the starting point, right? If you want to implement things on a quantum computer, this is where it all starts. And it's right now, it's still, I wouldn't say, it's definitely not, it's in infancy right now. With the quantum computing like field is in more of its adolescence, I would say. But it's growing very fast, but people are still looking for, you know, new candidates for what can be good qubits, and what are these complex problems we can solve, and can we even understand quantum systems better, and do they give us even more insight into quantum mechanics? So like, it's something we know quite a bit about to be able to build a machine like this at this point. But it's still something that, you know, is also mysterious to us, and it's teaching us new things every day. So what are the components of a QPU? So now you've seen this, but what actually is inside it now? Which part of this is the quantum computer, right? So the components, main components of a QPU include the physical computational qubits, of course. Then you have the control electronics, which are extremely, like, which are some of the most important components of the quantum computer. Then you have the classical compute hardware, which is used for holding instructions in memory, amplifying and managing input and output signals, and separating signals from noise. Now, what do we mean by this? So, like, let's just take the most basic circuit you can think of. Say you have like two qubits, you have a Hadamard, you have a CNOT, and you're doing a measurement, right? Hadamard and a CNOT. So you have two qubits, you have a Hadamard, which is a gate, and you have CNOT, which is a 2-qubit gate. Then you have measurement. So now if you measure these two qubits, which is absolutely necessary for any like quantum computing process, where do you store this information? So that's where the classical compute hardware is going to come. But as such, if you want to implement, say, if you have two qubits and you want to implement a Hadamard gate and you want to implement a CNOT gate, how do you communicate this? Like, right, it's everybody is using quantum computers via cloud. Nobody is actually going physically to some site and, like, you know, pressing some buttons or doing some sort of pulse engineering to be able to you know, implement a Hadamard or a CNOT or anything. Like, we write qc.h of 0 and then we do few different steps, but then the Hadamard is getting applied on the quantum computer, right? So these in between components, which convert, you know, what you send from a classical computer to a quantum computer, some of this is like related to what comes. So some of these interfaces will exist in the hardware, and they are part of the quantum processing unit. So that's what the control electronics does. And then you have the actual qubits itself. As you all know, IBM has superconducting qubits. So so the chips or the qubits are made of superconductors. So now this big, like, what to say, very fascinating looking machine is there. But if you actually like look into it, a lot of this is actually the dilution fridge, right? It's the refrigerator which cools down the qubit to make sure it's superconducting in nature. So the actual chips exist at the very base of the computer. So that's just a small piece of information for everybody to think about. This whole thing is not the quantum computer itself. Hello, am I audible? Am I audible clearly, or I just saw a message? Okay. So maybe it's a network side issue. So
You are
let's.
audible. No problem. Please go ahead.
Great. Great. Thank you. Also, if the slides stop moving at some point, also let me know, because that has happened previously. So if that happens, also please let me know. So yeah, so at the base of this, at the very base of this computer, you have chips. the size of your hand actually, and these are the quantum chips actually. So the everything else like that's above and that's looking so intimidating, like most of it is actually part of the dilution refrigerator, which helps to cool down your chips and make sure that they are still superconducting in nature. So if a QPU is at the core component of any quantum computer, the quantum chip is the core component of a QPU. So that's so like any advances we make in like building a QPU, a major part of it is going to come from the advancement related to the quantum chip itself. It is the core component of a QPU because that's the one which is giving the capability for you to say like say I want to build a 10 qubit circuit. My QPU needs to be able to support at least 10 qubits. So that 10 qubits is going to come from the quantum chip. So that say now today I want to do 10 qubits, tomorrow I would want to do 50 qubits. So so the growth of a quantum computer is related to the growth of the quantum chip in some sense, but also but also the quantum processing unit, of course, which is going to come in the intermediate stage, but then it includes other components. So the quantum process, so it also includes control electronics and classical compute hardware, which is required for input and output. So some of these components sit inside the dilution refrigerators, other components sit at room temperature beside the dilution refrigerator. So now all of these together form a quantum processing unit. So as we discussed, let's talk about what is at the heart of a QPU, which is the quantum chip. So QPUs contain a quantum chip similar in size to your average computer chip, like the classical computer chip. So it is a multi-layer semiconductor which is etched with superconducting components. So whatever you see outside the dilution refrigerator, it kind of takes you to those temperature where you can have where the material is at is able to is at superconducting, like it is superconducting at that stage, at that temperature. So the chip is composed essentially of physical qubits laid out in various configurations that are used to perform quantum calculations, and also the structures that and also structures to hold them in place. So one of the main things of what makes a quantum chip important is the connection between different physical qubits in the quantum chip itself. So I'm jumping a bit ahead, but I will mention this. So some of the so in the Eagle processor, which was like the active some time ago, and even the Heron processor, you have something called as a heavy hex. You have a specific topology. So this topology directly affects the kind of error correction you can apply on it. It also affects what kind of gates can be enabled on it. So we will discuss these things as like in upcoming slides, but the configuration of a physical qubit or the kind of connectivity it allows is extremely important in terms of it what capabilities the final quantum computer itself will have. So that is a very significant thing to keep to keep in mind, like how are the physical qubits in the quantum chip connected to each other. Then the chip is held at cold temperatures near absolute zero in the dilution refrigerator so that they can be superconducting. So this part is pretty obvious. So what are the components of a chip? So this is Osprey. This was released sometime I think in 2023, and it had 400 or maybe it was before 2023, but it had 433 qubits if I'm not mistaken. So you're looking at a chip which has almost about 400 qubits. So but yeah, so this layer in some sense you can think of it as the layer which holds the qubits, or it's also called as a quantum data plane. Then you have like a layer where you have the readout, where you are able to receive the readout information from these qubits. So if I measure a qubit, what is the state that I measure? So that will be received by the readout layer. And then you have the wiring, of course, which kind of connects you to the other components in the QPU. So that's a very high level sort of explanation. But if you want to kind of get into even more specifics, the different generations of IBM quantum chips, they have, the structure, this particular structure that we saw, this has evolved through different generations. So initially you had a very simple sort of architecture, but then like as with increasing, with as time goes on and you have like you have newer generations of chips, you improve the way you connect these layers, and you kind of improve you improve the interface between the layers so that you have better wiring and signal distribution, and so that the information that you receive has higher fidelity, and like you basically want. So what is the ultimate aim of doing a quantum computing, computing process on a quantum chip? You want to be able to create a physical, you want to be able to create a quantum state on a quantum chip, and you want to do some kind of processing on it, say apply some kind of gates, and then you want to measure that, and using the output you want to ultimately perform some kind of computation, right? So that is the ultimate aim. So so that process has to be faithful to what you find out theoretically. So if you have a, say, very simplistic so if you have a very simplistic structure for how you're building it, the computation process will be affected by noise and other factors. So to improve the fidelity of the compute and to reduce noise, to be able to have more features on to be able to provide more features, you want to improve the structure of your like chips, so that it can do a more high fidelity process, like it can conduct processes with higher fidelity, but also give you more features. Say I was only able to implement 3 kinds of gates in one generation chip. In the next generation chip, I would hope to be able to implement more gates between different qubits. So this is just to like still give a more high level explanation, but to give some understanding and context on what is being done, right? So the first generation of chips, we call it canary, and these were around 5 to 20 qubits each. So these were some of the names of the chips. You had IBM QX2, QX4, Yorktown, and IBM Q16 Melbourne. So these had ladder or linear k-qubit layouts, which is a way the qubits are connected. And these are early transmon qubits with minimal wiring complexity of the structure that you kind of saw here, right? Everything is very, very simplistic. You don't have much, sophistication going on here. But I mean, this was the first of its kind. So that by itself is pretty sophisticated. So I wouldn't say it wasn't sophisticated. This is where it all started. But this is a more simplistic and minimal sort of like say template of where people got started. So the second generation, this is quite significant. Um, you had Falcon and Hummingbird, like you have Falcon and Hummingbird like chips. So one thing is IBM quantum chips are named after birds, right? So Falcon R1 to R5. What is R1 to R5? I will explain in upcoming slides. But Falcon chips had around 27 qubits, and Hummingbird chips had 65 qubits. So you can see the scaling of what a quantum chip can accommodate. So in the first generation, you saw that we were only able to support 5 to 20 qubits, but in the subsequent generation we had like 27 to 65 qubits. So here we introduce the heavy hex lattice for better qubit connectivity and reduced crosstalk. So this heavy hex lattice is not just significant in terms of, supporting the qubit connectivity itself, but it is, a way of arranging the qubits in a compact form, making sure that, the errors which are coming up from the way they're connected is less, and the connectivity is sufficient that if I want to be able to implement a 2 qubit gate between, say, a qubit X and a qubit Y, there is some possible way to be able to do so, right? So if I have 65 qubits, actually, say if I have 5, okay, let us go back. So if I have 5 to 25 qubits, let's not even go up to 20. If I have 5 qubits, then I can come up with some sort of a layout where, multiple qubits are close by, and I can possibly implement. So one important requirement of 2 qubit gates is that they need to be connected to each other in some sense to be able to implement a 2 qubit gate across them. Now this is extremely important, and this will later on emphasize why quantum circuit compilation is very necessary. But for 5 qubits, you can imagine now, when even in this generation, when you get to 20 qubits, you can imagine that some qubits are going to be connected, but some qubits are going to be far apart, right? Now if I want to implement a C0 or some kind of 2 qubit gate between them, how would I do that? So this is something very important to consider, all the more so when you're scaling up your qubits. So when you're going to 27 qubits or 65 qubits, how are you going to implement, 2 qubit gates between two very remote, qubits? Say I create a 10 qubit circuit, but I'm saying I want to implement, I want to put a C0 gate between the first qubit and the 65th qubit. So how would this kind of make sense? I can physically label the qubits and call something the 65th qubit. I said it's a 10 qubit circuit. So, going a bit ahead, but then that's why the layout of a circuit is very important. So what is the layout? It is the way. Okay, let me just say this at this point. Now, when you have a quantum circuit which is virtual, in the sense you are coming up with an algorithm, how do you go from an algorithm to a implementation on a quantum device? You create an algorithm, you come up with a circuit for that algorithm, and then you map that circuit onto a quantum device, right? Now, in this mapping stage, before this mapping stage, when you've come up with this quantum circuit, now you have a virtual circuit. That's something we call as a virtual circuit. It's something that, say, you can draw a diagram about. But when you are actually implementing it on a quantum device, you have to say, okay, the first qubit here is going to be the first qubit I've labeled on the quantum device. Then the second qubit here is going to be the second qubit I've labeled on the quantum device. Third qubit, fourth qubit, and so on and so forth. But now, as I coming to the previous point, not every qubit is going to be connected with each other. So say I have a C0 gate between a first and 10th qubit, but they're far apart. Now, how do you actually implement a 2 qubit gate between the first and the 10th qubit? If I'm building a quantum computer, such a feature is necessary. It's not like it's a good feature to have, but it's okay if it's not there. It's a necessary feature. It needs to be able to implement this 2 qubit gate between these two qubits. Only then you can do the kind of computations that you want to do in order to implement your algorithm. So considering this factor, like 27 qubits and 65 qubits, the connectivity or the configuration and the layout of the way the different qubits are connected on a quantum chip is extremely important. And how do we learn more about this? We don't actually have a quantum computer like at our home, right? We, like the way we have a classical computer or a laptop in front of me, and I'm sure in front of every one of you, you have these you have a classical computer, but we don't have a quantum computer like that. So how do I actually understand what is the way that qubits are connected on a quantum computer? We use a quantum SDK, right? For whatever we want to try to talk to about the quantum computer, we use a quantum SDK like Qiskit or Qiskit runtime service. So this is something you can query from you can query. It's essentially called as a coupling map. So a coupling map on the level of Qiskit gives you information about how different qubits are connected. Now this again we will discuss as we go on, but just I'm jumping a little bit ahead so that you have context for why something we are looking at here is going to be important as we go through the course of the lecture, or also in the context of whatever you've learned so far as well. So something called as readout multiplexing is introduced in Hummingbird, which reduces the control line complexity. Then you have modularized chip architecture for scalability. Okay, this comes much later on, but then in Falcon, you have quantum volume of up to 128, in the R4 and R5, and clocks of yeah, okay. So some of this is like for the later generations, but yeah, these have served as production workhorses for quantum algorithm testing. So they also enabled practical execution of quantum circuits with moderate depth. So now when you come to the third generation and beyond, Eagle, Heron, etc. Now we kind of, I mean, if you had attended like QT-03 or 4 at some point, we discussed a few points about the Eagle and the Heron architecture. But like let us do it again because this is very important, right? So in Eagle, you have Eagle is the first processor where we went up to 100 qubits. So you have 127 qubits on an Eagle processor, and you had R1 and R3. So this R1, R3, this basically corresponds to something called as a revision, which we will actually look at in upcoming slides when we look at each chip individually. But you have scaled up heavy hex lattice here with advanced three-dimensional packaging with separated wiring, readout, and qubit layers. And these are retained transpond qubits, which have been optimized for stability over minimal error. Then you have like a good clocks here, up to 2400, and for R3 it is around 9904, which is optimized for error mitigation, not speed, which is why you see a bit of decrease. And then the median C0 error has also gone down, and this has also enabled execution of circuits with up to 60 layers using mitigation techniques. This has demonstrated utility class workloads exceeding classical capabilities. Now, this is extremely important because in 2023 we were able to come out with with a work which proved that which showed the utility of a quantum computer before attaining quantum advantage. And the way we did it is to use error mitigation in addition to the techniques that we are doing. So I mean, in addition to the normal optimization techniques for implementing a circuit more efficiently, etc. So this is extremely important in the context of what capabilities a quantum computer can support. Basically what that work showed is you can do calculations on a quantum computer which are beyond the capabilities of brute force classical computation, or it had not been done by it had not been computed classically before till that point. But we were able to find out the actual thing we were able to find out is computing some expectation values. And the way we did it even before getting like fault tolerant quantum computers is by using error mitigation techniques, which are I think quite well known at this point. But maybe I will try to discuss that at the end of if we finish everything else by the end, then we can come back to this point. So a note on IBM Heron processors. So the IBM Heron processors are have come after Eagle, and they have 156 qubits. Okay, the main thing here to understand, which is great about IBM Heron processors, is that there are two things. One is that they have tunable couplers, which virtually eliminate crosstalk errors and enhance overall performance. Right, so this is the first main thing about Heron, which makes it very important. They have this tunable coupler technology, which eliminates crosstalk errors and enhances overall performance. However, the even more important thing is that they have a modular design. Now, this came up in one of the previous slides. It's actually a typo there. I'm sorry about it. But here, Heron is the first processor where you have modular design. Okay, so modular design means that so what do we mean by modular design? So we as we go through different generations of chips, what we are doing is we are increasing the number of qubits that a specific chip can hold, right? But what about the fidelity of any quantum computing that you are performing on that chip? So Actually, if you see, after you had Osprey like you had chips like Osprey, and you had even Condor, which supported up to 1121 qubits. However, Heron is even more an even more significant innovation, because while giving very good quality of qubit of very good quality of fidelity with on computing with qubits, because of the tunable coupler technology, it also gives this modular design. What is meant by modular design? We no longer want to cram as many qubits into a chip as possible, but rather we are trying to build modular units which can be put together to form a bigger chip. So now the idea is that you take one Heron, you take another Heron chip, you put together, make a new chip. So the way you connect these two chips, and how you put them together, this is going to vary, and you kind of can improve that. How do you put all of them together? But the idea is that you have a modular design where you can put multiple units of Heron chip together, and you are building a bigger chip. So that's the basic idea. Now, in terms of performance, they have demonstrated a 3 to 5 time improvement in terms of device performance over the Eagle processor, and this is attributed to reduced error rates and enhanced gate fidelities. So what is gate fidelity? It means, say if I put say I have a qubit, say I have a couple of qubits which are connected, and I put a CNOT gate across the two of them. Now, whatever states I've prepared in this, I can kind of theoretically calculate what state should come out here in the other side, right? Now, if that is extremely accurate, you can say that the gate fidelity is very high. However, if it is not matching well, and it's a very poor sort of like when you read out, it's a very poor mismatch, then you can understand that the gate fidelity across these two qubits for that particular gate is slow. So that is the concept of a gate fidelity. Now, in terms of significance, it was introduced in December 2023, and it represents a new class of high performance processors in our lineup, and they serve as the foundation for IBM Quantum System 2, which is a modular quantum computing platform designed for scalability and integration with classical computing resources. Now, this is very important because at the current stage, we are in the utility era, but we are trying to march towards quantum advantage, and we're being ambitious in that we're not even waiting for fault tolerance to come in. What is fault tolerance? Fault tolerance is when you have proper error correction, and the fidelity of your compute is very high. Like basically, noise is not really affecting much of what you do. That's when we say we have fault tolerance. However, we've come up with various different ways in order to still do useful quantum computing even before we have achieved fault tolerance. And the way we are kind of trying to achieve this is through a strategy called as quantum centric supercomputing, where we are trying to integrate or interface or have a back and forth between like a quantum processing unit and say a HPC unit, which is already very good classical resource, which has helped us do a lot of things, right? So the idea of heterogeneous computing, especially in algorithms, like, so if you look at the way the research evolves, right, there is a lot of back and forth between different sort of units. So if you think about variational quantum algorithms, you know that it's kind of you have part of it running on a quantum computer, and then you do the optimization classically. In terms of even like other algorithms which have shown even more promise, sampling based quantum diagonalization being the latest one. So in this one, we are doing heterogeneous computing with one part of the algorithm running on a classical computer, and not on a quantum computer. And some results which we take from a quantum computer, we process them using a HPC, using a supercomputer. So with these two together, we kind of try to get useful results out of that. So this model of heterogeneous computing, which is evolving, requires that quantum computers are also able to interface well with classical computing structures. Because if you think about it, just because quantum computers are kind of becoming relevant now, it's not going to make classical computers which have gone through decades of research and optimization to be so performant, it's not going to eliminate their relevance over a single night. So with that in mind, it's good if a quantum computer can do well what it does well, and we use that in in addition to what a classical computer can do well, by coming up with a heterogeneous quantum algorithm which uses the traits of both these two different computing entities together in a more effective way. So with that in mind, this is a very sort of important thing to keep in mind, that quantum computers, as we develop and go on, need to have good, not just hardware but also software compatibility to be able to have a back and forth between classical computing resources. Now, before we I'll just have some water before we start discussing about some different chips a little bit in a little bit more detail. So canary is the very first one which we discussed, or which we looked at in the beginning. So the canary family comprises small designs containing anywhere between 5 to 16 qubits. It uses an optimized 2D lattice. That is, all the qubits and readout resonators are on the same layer. Now this R basically stands for revisions, and it corresponds to some kind of significant change in terms of the technology which has happened on that particular chip. So if you look at the revisions to canary, you have R1, where the initial 5 qubit design with resonators and qubits are all on a single lithography layer. Then in R1.1, which was released in May 2017, you have similar design processes to R, you have basically using a similar design process, you extend it to 16 qubits. Then in R1.3, you have you have a stripped down offering containing only a single qubit. Then we had the Falcon quantum processor, which has a quantum volume of 128. So this quantum, okay, by the way, quantum volume is not the same as quantum, like the number of qubits. So the number of qubits we discussed before, I think it was 23, right? So the quantum volume is, however, 128, and quantum volume is kind of a quantity which helps you gauge how much gates you can apply, how many qubits it can support, but also what is the size of the gates that, or how, what is the depth of the gates that you can implement on a quantum computer. So the Falcon family of devices, so these are good for medium scale circuits, and they serve as a valuable platform for demonstrating performance and scalability improvements before they're pushed on to larger devices. Now, for any processor, right, the native gates and operations are extremely important to look at, because most often these are sort of the quantities which will change across different devices. So in Falcon, you have CX, which is the C naught gate. You have identity, you have delay, measure, reset, RZ, SX, which is the square root of X, and you have X, you have if else, for loop, and switch case. Now these three are more like dynamic circuit capabilities, but these were supported in some basic version of the Falcon with some very basic features. Then we had egret, which has a quantum volume of 512. Now this brings innovations of tunable couplers onto a 33 qubit platform, resulting in faster and higher fidelity 2 qubit gates. So the first realization of the egret processor has demonstrated the highest quantum volume among IBM QPUs and a substantial improvement in 2 qubit gate errors. So this new quantum processor is like it gave a substantial speed up and fidelity improvement, and in 2 qubit gates, and while reducing readout errors essentially. Then we had Hummingbird, which has a quantum volume of 128. This uses a heavy hex qubit layout, and it allows up to 65 qubits. And what are the major revisions that happened? So this is the first. So this was the first attempt at supporting a large number of qubits, basically greater than 50. And then this was released in 2025. So we went from 50 to 65. Now so this improvement was previously demonstrated on Falcons, but then you also had more sort of technological improvements in terms of how you kind of So when you scale the qubits, it's not just about adding more qubits. You have to also still make sure that while you're increasing the qubits, you're still able to implement 2 qubit gates between different qubits. You're able to first of all cram that many qubits into this chip without disturbing the overall layout. And because you're putting all this in proximity, it shouldn't cause any issues. So these are all some things you have to take care of. So the final version has enhanced coherence properties. Now, coherence is also a very extremely important kind of concept if to understand in terms of a quantum computer, or even more fundamentally any qubit. So this is a coherence. The property of coherence is important, whether it is a superconducting qubit, whether it's a neutral atom qubit, whether it's a whether it's any type of qubit. Basically, a coherence is a quantity which tells you how long a qubit remains stable. A qubit is highly unstable by itself, or it's very sensitive, right? So it will not usually stay alive, or it will not stay with that quantum mechanical property, say in on state the entire time. So if it does stay, or basically a coherence is something that quantifies how long it stays in that, it retains its quantum mechanical properties, and it doesn't sort of die down, or become or collapse to a classical state. So when a qubit gets disturbed, you can think of and sometimes the environmental noise acts like a measurement, and it will collapse your state. When it collapses, it will either go to 0 or 1. So you're basically losing. So if it is, say for example, in a superposition, you're losing that property of the quantum mechanical property and the information that is contained in the superposition, right? So these sort of so coherence is basically a quantity which refers to this quantum mechanical nature of any qubit. How long can it keep that property alive? So in the 65, in the R3 version, all the 65 qubits had enhanced coherence properties. So that's something important to keep in mind. So then we had, of course, the Eagle processor at 127 qubits. It had more scalable packaging technologies, and so it also allows signals to pass through multiple chip layers. So it doesn't sacrifice on performance either. And the native gates in sorry. The native gates in Eagle include ECR gate, identity, delay, measure, reset, RZ, square root of x, etc. So you can look at the sort of revisions which were made to these as well. At qubit, at the qubit level, initially it was all similar to Falcon, but it was all initially similar to Falcon. In the R3, again, it had improved in coherence properties, but otherwise it was similar in design to Eagle R1. Then the latest one, which is Heron, at quantum volume 512, it supports 156 qubits, and it's an eagle-sized upgrade to egret that pulls in substantial innovations in signal delivery that were previously deployed on Osprey. Osprey was the 433 qubit quantum chip. So the signals required to enable the fast, high-fidelity 2-qubit and single qubit control are delivered with high-density flex cabling. So the native gate operations here are again different. You have CZ gate. So if you look at the native gates, right, so most of these are single qubit gates. However, you have you have 1 2-qubit gate. Here you have CX, right, in Falcon. In Eagle you had ECR, and in Heron you have CZ. Now if you look at, usually every chip has 1 2-qubit gate at least, and if you see, this is differing across different hardware. So this is important to keep in mind. So the first version of Heron was actually with 133 qubits. Even now, if you look at Torino has 133 qubits. The R2 is a revision to the original Heron processor, and the chip got redesigned to include 156 qubits in a heavy hex lattice. So so it also introduces new features to control some environment of the chip. So this way it improves the coherence and stability across the whole chip for all the qubits. Now let's look at the journey ahead in terms of the roadmap. So the green tick marks actually show the systems which have actually been completed. And initially we only had the development roadmap, but recently we introduced another innovation roadmap, which is necessary if you want. So like in terms, anytime in research, as you try to develop things, you are going to run into some kind of roadblock, right? When you run into a roadblock, what do you need? You need some kind of innovation or out of the box thinking to kind of support you to get through that roadblock. And that is the natural sort of way the innovation roadmap came about. So this innovation roadmap, in some sense, like it basically is going to come up with some kind of ideas or like innovations which will sort of float on top to the development roadmap. And that way we are going to sort of see improvements in what new is coming. So these are all sort of the targets which have been attained in the roadmap. So if you see, and in for the scope of this talk, I want to focus on mainly the hardware innovations which have been discussed, which can be seen here in black. So you have in the early stage, you had Canary, Albatross, Penguin, and prototype qubits for 5, 16, 20, and 53 respectively. Then we had Falcon, where we demonstrated scaling with I/O routing with bump bonds. Basically, the way the two so basically multiple layers of the chip interfaced, that kind of got improved such that the information flow across the chip is a lot smoother. Then there's the Hummingbird chip, where there was scaling demonstrated with multiplexing readout. Then you had Eagle, where you demonstrate scaling with MLW and TSV. Then we have Egret, where you have a tunable coupler demonstration. Then you have Osprey, Condor, Heron. You have increasing number of qubits basically. And we have Flamingo, the most recent one, where you have multiple herons put together, to be specific. And then Crossbill, where you have M coupler technology. Then we have more targets, right? I will discuss this further. So now let's look at the hardware innovations in a little bit more detail. So in 2023, the roadmap, like we wanted the end goal is basically to be able to develop first Starling, which was supposed to be the first large scale fault tolerant quantum computer. And this we hope to do by 2029. So the roadmap now reflects 2 more years of progress toward that milestone in 2025. We have introduced new hardware focused this thing on increased qubit connectivity and restructured our quantum software development plans around these 4 key objectives. Now these updates will be in the following slides. So IBM Quantum Nighthawk is this Nighthawk is going to be the most recent one, where we support a square lattice instead of a heavy X lattice. And like basically it is also expected, we hope that it supports more qubits or basically we hope that it can it supports more gates. Basically we should, so the size of the circuit you can build on a quantum computer, or the upper bound, is going to be determined by the depth as well, right? So this depth is going to be controlled by the number of, by basically how much depth of gate can you implement on the quantum computer. So then we hope to attain Starling in 2029 and Blue Jay in 2033. So this is, I would say, okay, just to end it on like a not so abrupt note, like these advancements which are coming up in the hardware, these need to be supported by performance software. Now, coming back to the point on what I said about, compiling quantum circuits to be able to run on hardware, you have to realize that, different when the structure of the hardware is different as we go on and on, the way you map your circuits also need to change. Sometimes it becomes more efficient, but then certain other challenges might come because of like the way it changes, right? So you need to constantly update your software such that it is able to run or do computations on the most advanced up-to-date hardware. So that is why the development of hardware and software also go hand in hand for the overall development of quantum computing as a field, and to be able to build a fault tolerant quantum computer by 2029. When you build that quantum computer, you want to be able to do good high fidelity operations on that. So this is an absolute sort of requirement. So I'll end this part of the talk on that note. I'll stop sharing and I'll take a few questions now. I saw that I think I noted that there were quite a few. So let's address those. Okay, yes, CLOPS refers to circuit layer operations per second. Are such processors available in market or only with IBM? So since this was a talk on near-term processors, we are actually right now not in near-term, we are in more of the utility era. But still it is important to understand the history and the evolution of quantum processors. So right now, actually, we only have devices which have more than 100 plus qubits. So it comes back to a very simple factor, right? If I can say, if I want to find out what is 13 plus 15, I can just do mental math for that. I will add 5 and 3, which is 8, and then the first two digits are going to be 28. It's a very simple calculation. I'm not going to pull out a calculator for that. But if I make it slightly more complicated, say I want to multiply two 5-digit numbers, then I might feel lazy and say, okay, let me open the calculator on my phone and, multiply those two numbers and see what the answer is. Of course, I can do it by hand, but it's faster to do it on a calculator, right? So that makes it a valid thing to do. Now, if you kind of keep increasing the complexity little by little, you can think that, say for a slightly more complex problem, you write a sort of Python program to find the solution. But you're not going to write that Python program to find out what is 15 plus 13. So that's just simple to solve using mind math. So with that in mind, quantum computer is a very sort of sophisticated device, which is very expensive, but it also offers a unique kind of math, right? You don't do normal mathematics the way you do on a classical computer on a quantum computer. Classical computer does say it is based on Boolean algebra. It is based on like Boolean algebra, whereas quantum computers are based on linear algebra. The math fundamentally differs on a quantum computer. So you want to use it for problems of appropriate complexity. So if you look at the kind of problems you're solving with say under 50 qubits, right? Those can be somehow managed to be done on classical computers which exist today, especially if you're only using say 20 qubits or 30 qubits. It can be a push, but with a little bit of sort of tweaking and tricks, you can implement it to run on classical computers, and that's very cheap. So you need to your problem needs to be appropriately complex to show that it is useful to use a quantum computer to solve that. So we see that only when you're using 100 plus qubits, it's useful to use a quantum computer to solve that. So there's a very famous adage by Jay Gambetta, who's the lead for quantum at IBM, and he says, if you're not doing 100 plus qubits, if you're not using 100 plus qubits, you're not doing quantum. So that's something to take to heart, as you all also kind of work in this field and try to come up with new algorithms. I would say that you need to aim to build scalable approaches. Say you come up with a prototype of an algorithm or a use case. In the beginning, of course, you can start at 20 qubits, 30 qubits, but the aim should always be to use more qubits and to solve a bigger problem size or something that's more complex, something that's difficult to use, or that is not trivial to do on a classical computer. So so like using 100 plus qubits is not like the absolute thing, but you have to really keep it in mind that the problem complexity or the way you're solving the problem on a quantum computer is appropriate to the kind of resource you're using, right? So yes, that's okay. Coming back to are such processors available in the market? Like, okay, these are all, whatever we discussed, these are all chips from IBM. So right now we have only processors with 100 plus qubits. So anything from Canary up to like say Falcon and the rest, you only have Eagle and above available to use. So yeah, that is to answer that question. I'm not sure what you mean by the concept of cluster qubits.
The question may be whether there are other companies also offering this thing. That may be the question also.
I'd
There
like,
are
okay,
other processors, right? Yeah.
yeah, some of them are kind of, I think some of them do offer like their backends for use, but not all of them. Some of them they do, I think, like offer. But so either the technology can fundamentally vary, they can be, say, neutral atom quantum computers, or yeah, it basically differs. It based on the technology, and different companies are at different stages of development. So I would say that yes, some of them do offer, but one thing I would say that is that, so simulators are not quantum devices. Okay, so simulators are devices which mimic a quantum computer, but they are built on top of classical computers. So simulator offerings in my, like, I mean, from what how I understand, simulators are not the same as quantum computers, because they're not actually built on the quantum they don't have those quantum mechanical properties. We can come up with ways to sort of mimic them, but it's when you scale and when you solve real problems, you will not have the same effects that you see on a quantum computer on a quantum simulator. However, quantum simulators are still useful. Before you run something on a quantum computer, it's a good practice, because classical computers are cheaper resources. It's a good practice to always run things on a simulator, do some preliminary analysis, and then make sure that when you're using your quantum computer, you use it as efficiently as possible. So yeah, that is one thing. Okay, I see the message asking me to take 5 minute break. I'll do it soon. I'm sorry, it's a bit late. The next session can be for half an hour. So yeah, I'll just take the rest of these questions like in maybe 5 minutes, less than 5 minutes. Okay, how many qubit computation can we do it in free tier in IBM quantum computer? So like it's not about the how many cube, okay, that is also included, but like it's more of a time sort of it's a time this thing you have 10 minutes free per month, and I believe you can go up to 133 qubits right now in the IQP cloud. Torino is offered as a free device, so you can go up to 133. I think there are two 127 qubit which are Eagle, and one Heron, which is Torino, for 133 qubits. Yeah, thank you. Any direct example? Okay, software layer abstraction, so that okay, with quantum processors are deeply integrated at math level. Changes in hardware would insist that software should be optimized with new available quantum math. Any direct examples that come to mind? So, okay, I can give you one example. So, the thing that changes is not really the quantum math, but how you bring the different components together, or for example, you're doing something extra. I will point you to the development of sample of V2 primitives. Essentially, we went from V1 primitives to V2 primitives. And V2 primitives, so if you look at the way the research evolved, a lot of research was aimed towards doing variational algorithms, right? Where you have parameter optimization. So the way you built your circuits, they needed to be able to support, this parametric, they needed to be able to support building parameterized quantum states. So this was not very efficient in V1. That is one point. The second point is when you start scaling up, you do say computations of 100 plus qubits, you need error mitigation in the near term to be able to like get good results, get useful results. Yes, you will incur a sort of classical overhead, but if it is improving kind of your result, it is still useful to do, right? So like in V2 primitives, like so basically going from V1 to V2 primitives, one of the major changes that we saw was that in V2 primitives development is that they supported parameterized workloads better. So the way you construct your circuits, you didn't have to make multiple copies. You could do it in a more efficient way, and you could also like it also had it also had inbuilt error mitigation options to be enabled. So that is a good, I would say, example for this one. Yes, there is a way to calculate quantum volume. You can find some papers on arXiv for that, or there are also some press releases which give you some idea on how it needs to be done. It's something you can find. When I share the material, I will try to put in some links for that. Okay, so what is CLOPS? CLOPS is circuit layer operations per second. So the way you have flops in like classical computing, CLOPS is a sort of it's a quantity to measure how many circuits you can implement on a quantum device. So basically, uh, so it's okay. There are more CLOPS and CLOPS related quantities, but essentially, how fast or how much, like how well can a device support running a specific sort of size of circuit while being run? So, okay, yeah. I think right now we should take a break. It's almost 3:12. Let us reconvene. Like let's take maybe we can take 10 minutes break, I think. I'll maybe get back to some of the other questions. But yeah, let's take a break. Shivansh sir, Pili sir, can we take a break now?
Yeah, yes, ma'am. We can take a
Sorry.
break and then you can take a few hours extra, maybe a few minutes extra
Okay,
today,
thank
maybe 4 10 that's so,
you. Sure, sure.
okay.
Okay, thank
We'll
you.
start at
A bit.
3:20. That will be better, 7 8 minutes, right? And then go up till 4:10 or something.
Sure.
Yeah.
Okay.
Thank you.
Okay. Thank you, everyone. Let's take a break. Shall we reconvene at 3:30? It's 3:13 right now. Let's reconvene at 3:30. Like everyone will have like a 10 15 or 3:25. I think a 10-minute break should suffice.
Okay, ma'am. 3:25 should be fine. You can go until 4:15. Yeah, that's
Okay.
fine. Thank you.
Sure. Thank you.